Okay, the streaming started. Okay, so you all are already familiar with what is dot product in R2. Yes or no? So you all are familiar with dot product, right? How do you do dot product in R2? Suppose you have two vectors. Okay, so let's say x1, y1 and x2, y2. What is the dot product of these two vectors? Yeah,
x1 x2
yeah,
plus y1 y2.
that's y1, y2. Okay, so using dot product, so can we find angle between two vectors? We had some formula, right? Using dot,
Yes, ma'am.
yeah. So
Yes,
using
yes,
this inner product, first of all, we defined some norm, right? How did we define norm using inner product? So norm of, let us say, x comma y. How do we define?
under root x
Square root
square
of,
x.
x1 square plus y1 square.
so here x comma 1 simply x square plus y square, right? So which is actually x comma y dot x comma y. So this is how we define norm. So using a dot product, we can define what is the length of a vector, right? So this is the length of a vector, right? We can define length, and we can also define what is the angle between two vectors. We can find the distance between two vectors. All this, if you recall, we have already done using dot products in R2. Okay, so how did we give the motivation for vector spaces? Let's just quickly go back. So what we did, we first took what is happening in R2. So if we had two vectors, how to add them, how to do the scalar multiplication, right? So addition of two vectors, how to do scalar multiplication, all these properties of vectors we first saw in R2. And then we just collected all these properties, summarized them, and then whatever set satisfies these property, we called it as vector space. Do you remember this part? Yeah, so this is how we got the motivation to define vector spaces using the already known properties in R2. We extended it to a general set and we called it as vector spaces. The exact same thing we are going to do now for inner product spaces. So how to define length of a vector, or what is the direction or angle between the vectors, or what is the distance between two vectors, all this we have already defined in R2 using dot products. Now, how to extend this for any Fn? Okay, or even more we can do, but here we are mainly look at Fn. Okay, so that generalization is what is called as inner product spaces. Okay, so extension of the dot product to any general vector space Fn is called inner product space. How are we going to do? We will see it step by step. Okay, so we already have seen this defining this magnitude is nothing but length, right? Magnitude is nothing but length. Okay, by direction or angle we are talking, direction is also telling about angle only. So here this direction tells about angle between the vector and the x-axis, and angle in general means between any two vectors. Okay, and distance in the sense, suppose this is a vector u and this is a vector v, what is the distance between these two vectors? Okay, what is the distance between these two vectors? So how do we find these things for a general Fn? Okay, fine. So now, uh, exact same definition, but we are going to generalize it for Cn first of all. So let's say we are going to define Euclidean inner product between two vectors in Cn with this symbol inner product u comma v in this way: u1 v1 bar plus etc un vn bar. Okay, so this is the Euclidean inner product or the standard inner product. Okay, so this is the usual way and it satisfies the following properties. What are they? Inner product v comma v is greater equal to 0. Always it is greater than equal to 0. It can never be negative. Why it cannot be negative? Because it represents length. Here you see inner product v comma v is similar to dot product of these two vectors. Like, let's call this, suppose let's say this is your vector u, then what is this actually? square root of u dot u, right? So u dot u is actually representing length. So can length be negative? It can never be negative. It is always non-negative, right? So if there is nothing to measure, then the length we define it as 0, and if it is there is some magnitude, then we are defining the length here, right? So it's always non-negative. That's why here you see in a product v comma v also is defining a length or magnitude, and hence it's always non-negative, and it is 0 only when v is 0. Okay, and then we have linearity with respect to the first variable. So what is the linearity with respect to first variable means that, so this is the first argument, and this is, so sometimes it says as argument better than variable. So this is the first argument, this is the second argument. So with respect to the first argument, here we see linearity. It means what? If you have au plus bv, then you can first of all split them. So the first step is that au plus bv comma w is equal to au comma w plus bv comma w, and then you can bring out the scalars a times of u comma w plus b times of v comma w. Okay, so in this case you see that this property is called the linearity in the first argument. Okay, and the next thing is that conjugate symmetry. Conjugate symmetry means inner product of u comma v is inner product of v comma u whole bar. You have a bar here. Okay, this is conjugate symmetry. Okay, so all this, remember, these are all for Cn. Okay, and there are few more things we can note. If one of the vector is 0, then the inner product becomes 0. Okay, and additivity in the second variable holds. Okay, so just like we saw additivity is there for the first argument, we have additivity in the second argument as well. And then what happens to scaling with respect to the second variable? So this one, you see here, inner product of u comma lambda v is equal to, let's just flip it. If we flip according to conjugate symmetry, what we will get? Can you say? Can you say
You,
you apply conjugate symmetry and flip? What will you get?
conjugate
Yeah,
symmetry.
lambda v comma u
you have to flip these. Yes, yeah,
Lambda
and then you have a
bar whole
bar.
bar.
bar. Yeah, and then now you apply the property we are using here. How, when you take out a scalar, you can take out a scalar. So when we take out the scalar, again you have a whole bar. So you have lambda bar inner product v comma u again bar. Now can I flip this again? Again let's apply conjugate symmetry, and this will become what?
UV.
uv. So you see inner product u comma lambda v is lambda bar u comma v. Okay, is that fine?
Yes, ma'am.
Yes, ma'am.
Okay, so now similarly, can you tell what about the linearity in the second argument? What will happen? Can you do something very similar to what we did here? Yes, I can zoom the screen.
Yes, ma'am.
Can you do something similar to what we did here? How to do? First, flip the argument. So if you flip, what will happen? AV
A
plus
plus
BW, comma U, and then you have a
whole
bar,
bar.
right? And then you know that you have linearity in the first argument. So apply the linearity here. So if you apply the linearity, you will get V comma U plus B times of W comma U, and then you have a whole bar. And then what? You can, inside the complex conjugate, you can easily split things, right? So you have A bar in a product V comma U bar, and then B bar in a product W comma U bar. So you have A bar. Again, let's apply conjugate symmetry to these two things. So U comma V plus B bar in a product U comma W. So what's happening here? You see, Inner product u comma av plus bw, when this a and b comes out from the second argument, you will have a complex conjugate for the scalars a and b. Okay, so if you are having Rn, then you will have symmetry, because in Rn, what is the complex conjugate of a real number? It's the same, right? There is no change for the real number. So if you are having Rn, then you are having symmetry. Okay, but in the case of Cn, you will have conjugate symmetry. Okay, and linearity in case of Rn, it is linear in both arguments. Why? Because you see again the same thing. If a and b are real, then a bar is equal to b. So it means you will have linearity in both arguments, right? And linearity, but in the case of Cn, you will have linearity in the case of first argument, and this is called conjugate linearity. What I have written here, this is called conjugate linearity. You have conjugate linearity in the second argument. Okay, and then you have positive definites. This is positive definite property is same for both. It is non-negative and zero only when the vector is 0. Okay, so this is what you should know about inner product in both Rn and Cn. Okay, is that fine? Yeah. Okay, so what is an inner product we have seen? So this is an example of a specific inner product which we call as the Euclidean inner product. Suppose, let's say your function here f of u comma v is defined like this. First of all, note that this inner product, okay, so you are taking two elements. So where is this u from? U is from Cn and v is also from Cn. So Cn cross Cn. You are taking an element from u Cn cross Cn and mapping it to an element in C. Right? So this is a function from Cn cross Cn to C. This inner product u comma v. Okay, fine. So same way we are taking some other function from C3 to C3 cross C3 to C, defined in this way. Okay, where u is this and v is this in C3, and this bar represents the conjugate. Now, which of the following options are true? F satisfies the conjugate symmetry condition of the inner product. What is meant by conjugate symmetry? Can anyone tell? What is meant by conjugate symmetry? F of u comma v should be equal to what? See, inner product u comma v, conjugate symmetry means what did we have? Inner product v comma u bar, right? Instead of this inner product, now you have f. So just replace inner product with f and tell me what you should have if you should have conjugate symmetry for f. Can you tell me? It's okay even if it's wrong, just try.
Ma'am, if v of u bar.
Okay, so this is the conjugate symmetry of f, and we want to see whether it is true or not. Okay, how to check that? So we have to first calculate what is f of v comma u. So according to this formula, what is f of v comma u? Can you tell? According to the formula given here. So in place of u, you have v, and in place of v, you have u. That's all. So can you quickly tell what is f of v comma u?
1 into u1 bar
You are
plus 2
2
v2
v2 plus u2 bar.
Plus 3 v3 into
u2 u3 bar.
okay, so now you have got this. Now what is the conjugate of f of v comma u? So it means we have to take conjugate of the whole thing. So v1 u1 bar plus 2 v2 u2 bar plus 3 v3 u3 bar, whole conjugate. So now inside the conjugate, we can split the terms. What is conjugate of conjugate? Z bar, again bar is equal to Z, right?
Z.
Yeah.
Z.
Yeah, so using that we will see that you can have, this is V1 bar U1, then V2 bar U2, and then V3 bar U3. All right. So then you will have, so multiplication changing position does not change anything, right? So multiplication of two complex numbers. So I can again rewrite them. So if I rewrite, what did I get again? So this is nothing but,
F
this is
of U,
nothing but,
comma V.
so does F satisfy the conjugate symmetry condition? Yeah.
Yes,
So
ma'am.
this property is the conjugate symmetry of F and it is satisfied. Okay. So the second property, what is positivity for F? What does it mean? F of U comma U should be greater equal to 0 for all U, and F of U comma U equal to 0 only if U equal to 0. Okay. So these are the conditions for positivity. So for that we need to find what is F of U comma U. Can you say what is F of U comma U?
So in place of U, V will place U.
So you have U1 U1 bar plus 2 U2 U2 bar plus 3 V3, sorry, U3 U3 bar.
U3 bar.
So what is Z into Z bar?
1.
No, x plus
Wait.
iy into x minus iy. What is that?
X square plus Y
You
square.
get x square plus ixy minus ixy.
Square.
Again, minus I squared is 1, so plus y square. So it is x square y square, right? And it is same as mod z square. Is that
Yes, ma'am.
correct?
Yes, ma'am.
Yes, ma'am.
Yeah. So you can replace u1 bar with mod u1 square plus 2 times of mod u2 square plus 3 times of mod u3 square. Is that fine? Yeah. So if we have mod less, then you know that it is always non-negative, right? And it is equal to 0 only when all the three entries are 0. So do we have positivity?
Yes, ma'am.
Yeah. So second option is also correct. Okay. And then how to check the linearity condition of the inner product, whether F satisfies the linearity condition. What is the linearity condition? This is the linearity condition. So we are checking the linearity in the first argument. So linearity of F, it means F of AU plus BB comma W should be equal to, can you say what is that? A times
A times U comma W. Oh,
plus B times
V
F
comma
of,
W. V comma W.
okay. So this is what we need to check. Okay. So first, what is F of AU plus BV comma W? Okay. So note that here, what is AU plus BV? It is nothing but AU1 plus BV1, AU2 plus BV2, and then AU3 plus BV3. So this is first of all AU plus BV. right? Now we will apply this formula. So if you apply the formula, you will get, so AU1 plus 1 times of W1 plus 2 times of, that's the formula, right? Plus 2 times of, oh, there is a bar for W1. AU2 plus BV2 W2 bar plus 3 times of AU3 plus BV3 W3 bar. Up to this, is it clear? The linearity part? Yeah? Okay. So next we have to simply multiply each term. So AU1 W1 bar plus BV1 W1 bar plus 2AU2 W2 bar plus 2BV2 W2 bar plus 3AU3 W3 bar plus 3BV3 W3 bar. Alright, so now what we are going to do, we are going to pick the A terms separately and B terms separately. So if we are picking out the A terms separately, you have U1 W1 bar plus 2U2 W2 bar plus 3V U3 W3 bar. And then B terms, V1 W1 bar plus 2 V2 W2 bar plus 3 V3 W3 bar. So this means you have A times of, what is this term? Can you tell now?
F of UW.
Plus B times of F of,
VW.
okay. So we prove the linearity of F. So all the three properties are satisfied. If all the three properties are satisfied, so you have positivity, linearity and conjugate symmetry. If all the three properties are satisfied, so these are the conditions for inner product. So is this an inner product then? Yeah. So if all three are there, then this implies that F is an inner product. So what about option D? Incorrect. Okay, so when we have all these three conditions, then we say that it is an inner product. Okay, and here for this function all the three are there, so it is an inner product. So option D is incorrect. Okay, so given any function like this, if all the three conditions whatever we just verified, similarly if you are able to verify and see it is true, then that will represent an inner product. Is that clear? Yeah. Just like linear transformations, we used to check two conditions, right? The additive property and then the scalar multiplication property. Similarly, for inner products, we have to check these three conditions. Is that clear?
Ma'am, if
Yes.
one is not satisfied, then that is not inner product. No, ma'am?
Exactly. Even if one of the condition fails, then it cannot be an inner product.
Oh,
Clear? Yeah, that's what exactly I said. If one of the condition fails, then it is not an inner product. Okay, fine. Okay, so you remember how did we define norm? So norm is the positive square root of u dot u for the dot product, right? So the same thing happens here as well. So if you have any vector v in Fn, the norm of v denoted by norm v takes a non-negative real number defined as square root of inner product v comma v. Already we know that inner product v comma v is non-negative for any v, so the square root is well defined. Okay, so here is an example given to you, I comma 2i comma 3. So first of all, this is a vector from which space, can you say? This is a vector in
R3.
C3.
C3. Sorry.
Because you have imaginary numbers, right? Yeah. So now you have, see, this is, let's say this is your u1, u2, u3, right? So how do you do the inner product? U dot u. So if you want to do u comma u, what's the formula? u1 u1 bar plus u2 u2 bar plus u3 u3 bar. right? So that's what they have done here. U1 U1 bar plus U2 U2 bar plus U3 U3 bar. Okay, and then they have applied the conjugate for each of the numbers and then computed the value. Is that clear? Computing the norm of a complex number. Okay, and then we know that if you take square on both sides, then norm v squared is inner product v comma v. Okay, and norm v is 0 if and only if v is 0. Okay, and when you have a scalar inside the norm, it comes out with a modulus sign. Norm of lambda v is mod lambda times norm v. Remember, norm is always non-negative. So because it is non-negative, whenever a scalar is inside, when it comes out with a modulus. Is that clear? Okay, so just in a similar way, how to compute a norm in R3? Can you find the norm of u squared for this vector? This is a very simple problem.
Ma'am, then scalar will
Can
be
you-
always positive. Scalar.
Here,
Yeah, ma'am.
that's what I'm saying. Even if, for example, here you have, suppose let's say you are having modulus of minus 5 times of v, then you will of norm v. Okay, that minus will become plus
Okay, ma'am.
because you will take modulus. Okay, fine. Okay, so what about the norm of this vector?
50. Under root 50.
Yeah, 3 square plus 4 square plus 5 square. So which will give you 9 plus 16 plus 25, which is 50. So norm u square is 50. Is that correct? Did you all get the same answer?
Yes, ma'am.
Okay, good, good. So see, how do you calculate distance between two vectors in R2? Just recall. Okay, so recall, suppose you have a vector u and you have a vector v. Okay, so these are the two vectors. So this is your vector u and this is v. Okay, so your vector v, u and v. Now you want to calculate the distance between u and v. So u, v. How did we calculate norm u minus v? So norm u minus v means you have x. So this distance between x coordinate is x2 minus x1 and distance between the y coordinate is y2 minus y1. Right? So now how to calculate the norm between these two vectors? It is square root of x1 minus x2 whole square plus y1 minus y2 whole square. Okay, because you are having a right angle triangle like this. So this is x2 minus x1. This is y2 minus y1. So according to Pythagoras theorem, what should be this? So let's say this is A, this is B. So what is C then? C is equal to square
B
root of
square plus B
A
square.
square plus, right, using Pythagoras theorem. So the same property is used here. So the distance between u and v, norm of u minus v, is this. Okay, so the exact same concept we can apply here as well. Okay, so how do you calculate the norm of u minus v here? Everyone calculate it quickly. Norm of u minus v. So instead of just 2 x1 and x1 y1, here you have x1 y1 and z1. That's all. So how do we calculate? Can anyone say?
1 minus 4 whole 1 minus
1
4 whole
minus,
square plus 2 minus 6
yeah,
whole square. 3 plus 3 whole square.
yeah. Calculate it and tell me the final answer.
Under root 61. Square root of 61.
Are you sure? It's 9 and 16 and
36.
36.
25 plus 36.
25, 36, yes. It's 61. Okay, square root of 61. Okay, fine. So the next thing is that we are going to see what are orthogonal vectors. Okay, when do we say two vectors are orthogonal? So two vectors are orthogonal if their inner product is 0. Just like we saw in the case of R2, in R2 we say that two vectors, right? In R2 you say that whenever you have two vectors, right? So two vectors are said to be orthogonal. For example, any two vectors like this when the angle between them is 90 degree, right? So for example, x comma 0 dot 0 comma y, any vector like this, they are on x and y axis, then so you know that their dot product is 0, right? So we say that these two are orthogonal. So inner product u dot v dot product is 0. The same way, if the instead of dot product, if the inner product is 0, then we are saying two vectors are orthogonal. Okay, so extending from R2 geometrically, we think of orthogonality similar to being perpendicular. Okay, so if inner product u comma v equal to 0, then inner product v comma u should also be 0. Okay, so u is perpendicular to v. This is the notation for orthogonality. Okay, and you know that inner product 0 comma v equal to 0, so 0 is orthogonal to all vectors. Okay, and suppose a vector is perpendicular to itself, what does this mean? It has to be the 0 vector. There is no other way a vector can be perpendicular, because v is perpendicular to v means what will happen? If v is perpendicular to v, then according to this property, inner product v comma v equal to 0. So we know that v inner product v comma v equal to 0 if and only if v is 0, right? So that's why v is perpendicular to v. V is orthogonal to v if and only if v equal to 0. Is that clear? Yeah? All right. So the next thing here, we have a very simple problem. Which of the following vectors in R3 is orthogonal to both the vectors 1, 0, 1, 0, 1, 1? Okay. One straight way is that you can simply check the dot product between the inner product between any two vectors, whether they are orthogonal or not. So let's say this is u and let's say this is v. Okay, so here you have some vectors. So what is inner product of u with this vector? So this is one way of checking, like one by one you can check. The other way, let me tell everyone, listen carefully. This is something very important and this is what we are going to use in many places. So everyone listen carefully. Suppose you are having two vectors and you want to find all the vectors which are orthogonal to these two vectors. How will you find? So let w be some vector x comma y comma z and such that u 0 and vw is 0. So what will you get? So inner product of 1, 0, 1 with x, y, z. What is the answer for this? When you do the inner product, what will you get?
X plus Z.
It's an R3 only. Okay. Similarly, what is 0, 1, 1 inner product with x, y, z?
Y plus Z equal to 0.
Okay. So what is the relation we get? X is equal to minus z, y is equal to minus z. Okay, so it means what? If we suppose we put z is equal to 1, then we can get 1 comma minus 1 comma minus 1 comma 1. Or if you want to write the general form if you want to write, so it is the set of all x comma y comma, or let's say let's put some alpha for z. If z is equal to alpha, then it is minus alpha, alpha, alpha in R. Okay, so this is the set of all vectors orthogonal to both u and v. Okay, so any vector orthogonal to u and v should be of this form. Now, without even verifying for each single vector, which of the vector is in this form? Which of these four vectors is in this form?
C.
Right? So alpha is equal to minus 1 in this case. So you get 1 comma 1 comma minus 1. Right? So the other options are not satisfying this form. Is this clear how we did this? Is that clear? Yeah? Yes or no?
Clear, ma'am. Yes, ma'am.
Okay. Good. Okay. So now consider two orthogonal vectors a comma b in R2. If a plus b and a minus b are orthogonal, then which of the following option is correct? So first of all, if two vectors are orthogonal, what do you know? So let's say this is u and this is v. What do we know? If two vectors are orthogonal, what do you know?
Ma'am, inner product are 0.
Inner product should be 0.
Exactly. Yes. So it means a plus b into a minus b is equal to 0. Now apply the orthogonal property here, linearity of R2. So if you are in R2, you know that it is linear with respect to both first argument as well as second argument. So how can we split this? So first apply linearity for the first argument. So you will have a comma a minus b plus b comma a minus b equal to 0, and then apply linearity for the second argument. So you will get a comma a minus a comma b plus b comma a minus b comma b. Now since we are in real, what do you know about what is the relation between a comma b and b comma a? We are in real.
It's same, ma'am.
Same, right? So if they are same, then these two we can cancel it out. Right, these two can be cancelled out. So what is left? You have inner product a comma a equal to inner product b comma b. Right, so minus when it comes to the other side, norm a square equal to norm b square. So norm a equal to norm b. Yes or no?
Yes,
Correct, right?
ma'am. Yes.
So option B is correct. Clear? Okay, fine. So we have already seen Pythagoras theorem in general in R2. What is the Pythagoras theorem? Right? So what is the Pythagoras theorem in general? So you know that if you are having something like this, okay, and then another line, maybe I'll draw it visual thing. So you have some, not exactly, yeah. So you have this is u, this is b. Say what does Pythagoras theorem say about the other side, the hypotenuse side? Yeah,
Root over u square plus g
square
square.
root of,
Under root square plus
U
s.
square
yes.
plus g square.
Okay. So now suppose let us say, so if you take the square, then what happens? So this is what you will get. The square of this term is simply u square plus b square. Right? So the exact same thing is written here. Norm of u plus b square is equal to norm u square plus norm b square. But remember, this is true. This condition is very important. This is true only when u is perpendicular to v. This perpendicularity we need. Otherwise, this we cannot tell. Okay, the perpendicularity is very important. Okay, remember this part. Okay, so whenever we have perpendicularity, then we have this Pythagoras theorem. And what is the Pythagoras theorem saying? Norm of u plus v whole square equal to inner product of u plus v comma u plus v, and then we split the inner product using linearity. And you know that if inner product u comma, if these two are orthogonal, then you know that inner product u comma v equal to inner product v comma u equal to 0. Right? From here we know this, and we are applying it here, and then you are left with norm u square and norm v square. Is that clear? Yeah. So this is Pythagoras theorem for inner product space. And the next thing is that we can do orthogonal decomposition. What is meant by orthogonal decomposition? First of all, what is meant by decomposition? Decomposition means we are able to split a given vector into two parts. That is decomposition, splitting them. But what is meant by orthogonal decomposition? We are splitting it in such a way. So let's say you are splitting it as u1 plus u2. This is decomposition. And also I am splitting it such that u1 is perpendicular to u2, then it is orthogonal decomposition. Okay, how to do orthogonal decomposition is what we are going to see here. Okay, let us say you are having a vector u, and we want to find the orthogonal decomposition of u. Okay, so the technique we are going to do is that we are going to add and subtract the vector cv. Okay, we are going to add and subtract the vector cv. Okay, so if we are adding and subtracting from the figure, can you see that for an appropriate c, this u is exactly perpendicular to cv? Okay, so remember that if it is orthogonal, then the inner product u minus cv, this vector u minus cv is orthogonal to v. Okay, so this is your u minus cv, right? So u minus cv is orthogonal to v. Okay, so u minus cv is orthogonal to v, and then when we split them, you see that this is equal to 0. So inner product u comma v minus c times of inner product v comma v equal to 0, and then I can bring the negative to the other side. So you see that c is equal to inner product u comma v by norm v square. Is it a bit too much, or you are able to follow? If you want me to explain again, I will do it. Shall I explain it again, or is it clear?
Not clear.
Sorry, what?
Ma'am, clear. It is.
Not clear, ma'am.
Clear.
Doubt.
Not clear, ma'am.
Okay.
No, ma'am.
Okay.
Not clear, ma'am. Please explain.
So for those who find it not clear, let's see it again. Okay, we want to see whether we are able to find a c such that u minus cv is orthogonal to v. Okay, I want to see whether I'm able to find a scalar c such that when I verify u minus cv with inner product with v, I'm able to get 0. Such a c I want to find. Okay, so this is the condition I'm imposing. Okay, so u minus cv comma v equal to 0. So can find c such that this happens. Okay, this is what I want to check. Okay, so when I'm doing this, I am seeing that if I'm then splitting the inner product, then I will get inner v minus c times of inner product of v comma v is 0, and then what? And then bringing this term to the other side. So inner product u comma v is c times of inner product v comma v. Now what is inner product v comma v? Norm v square. So then I can bring this to the denominator here. So c is equal to inner product u comma v by norm v square. Okay, so for this particular c, my inner product u minus cv comma v is 0. So only for this c, I will have this condition. Okay, so when my c is equal to this particular value, these two vectors are orthogonal. Okay, your v and u minus cv are orthogonal. Okay, fine.
Yes, ma'am. It is
So
clear.
in this case, yeah, so in this case, so what are we going to see here for u comma v in Fn with v non-zero, we have u equal to Cv plus W. So how I am splitting u now? U is equal to Cv, and this is the vector I am calling it as W. This part I am calling it as W. Okay, and this part is Cv plus W, where C is this number which I calculated and W is u minus Cv. Okay, and you know that Cv and W are and V and W are orthogonal. Okay, if V and W are orthogonal, you know that Cv and W are also orthogonal, right? So this is an orthogonal decomposition for U. Okay, fine. So next we have two inequalities, I guess. Yes. So quasi-squares and triangle inequality. Triangle inequality is something you see very common even for modulus function, right? Modulus of u plus v less than or equal to mod u plus mod v. The same inequality you have for norm as well. And the other thing is the quasi-squares inequality. This is used in some of the proofs. Okay, so this is an important inequality for norms. Okay, so what is the inequality saying? Suppose you are having two vectors in Fn, then modulus of inner product u comma v. Remember, inner product u comma v is an element in F. So you will have for an element in F, it is a scalar. So for scalar, we only have modulus. Okay, you may think why here on the right hand side you have norm, on the left hand side we have modulus, because these are vectors. U and v are vectors, and this is a scalar. Okay, so these are vectors and this is a scalar. So for scalar we will have modulus, and for vectors we are having norm. Okay, so let's assume that v is non-zero. If v is non-zero, then you know how to write an orthogonal decomposition. So for orthogonal decomposition, you know that u is equal to Cv plus W, right? So C, this is the C, if you remember, this is your C, right? The value within the box is C. Cv plus W, and W is u minus Cv, right? So if W and V are perpendicular, what do you know? You can apply Pythagoras theorem. According to Pythagoras theorem, if u and v are W, then the norm, sum of the norm is equal to individual squares, right? So norm u square is equal to norm Cv square plus norm W square, because here V and W are orthogonal. This part, is that clear? See, V is perpendicular to W. This means that Cv is perpendicular to W. This means that Cv plus W norm square is equal to norm Cv square plus W square. Okay, according to Pythagoras theorem. So what is this Cv plus W? Cv plus W is nothing but U. Okay, and then now this is a non-negative value, right? So norm of anything is a non-negative value. So if I am just leaving out this, then you know that this part is greater equal to norm Cv square, right? And what is norm Cv square? C, you already know that it is inner product u comma v by norm v square. So I'm writing the value of C here. This part, if you want, I'll write it here. So here norm into C is inner product u comma v by norm v square. This is C, and then you again have v to norm v square. So now this is a scalar. So I'm bringing out the scalar outside. So you have modulus of inner product u comma v by norm v square. Already you have a norm v square and then a square here. So norm v power 4 into norm v square. So this is the other v. So now you can cancel these powers, and then you have, because v is non-zero, so denominator is valid. So you can cancel out the powers and you will have norm v square. So is this calculation clear for everyone? What we have done here, is that clear? Yes? Yes or no? Is it clear? If not, please tell me. Or if it is clear, also tell me. If you keep quiet, I don't understand what's going on. Okay, it's clear, right?
Yes, ma'am.
What
It's
about the others? Are you still there in the class or you are sleeping? Okay, fine. So the next, so someone asked for some problems. So you want problems like this, or you ask problems for what? One of you have asked
for C.
Sonali, I
For
guess.
C. What will be the question for C? To
For
find the value of C.
oh, this kind of orthogonal decomposition.
Yeah, yeah.
Okay. So we have another session on Friday. Maybe at that time we will solve a specific problem for this.
Okay, ma'am.
All right. Okay. So today, how far should we continue? I guess we will continue till this orthogonal vectors, and then we will stop, and then we will continue from orthogonal basis in the orthonormal basis in the next session. Okay. Fine. So parallelogram identity inequality, what does it say? So here parallelogram inequality says that norm of u plus v whole square plus norm of u minus v whole square is equal to 2 times of norm u square plus norm v square. Okay. So here, how are we getting this? Hold on, did I paste the proof of something else here? Norm of u. Okay, so the same thing we can use, and then you will get 2 times. Yes, it's correct only. So here you see that here it's actually an inequality. Okay, so if you have any two vectors u and v, okay, so norm of u plus v whole squared and norm of u minus v, minus means v is here, so this is your v, minus v means it's on the other side, right? So your minus v is on the other side. Okay, so this is your u and this is your v, so this will be your u minus v. Okay, so norm of u plus v whole squared plus norm of u minus v whole squared, so and then this is norm u and this is norm v is less than or equal to 2 times of norm u square plus norm v square. Okay, fine. So how do we, so this is called parallelogram inequality. So how do we prove this? So norm of u plus v whole square is equal to norm u square plus norm v square plus 2 times of real part of inner product u comma v. How did we come to this? Can anyone say? It is a straightforward thing we can see. So norm of u plus v whole square is inner product of u plus v comma u plus v, right? So when we split this, it's inner product u comma v plus inner product v comma u plus inner product u comma v plus inner product v comma v, right? Now this is norm u square, this is norm v square. Now what is this? So
It will be
let's say
0,
this
0,
is
ma'am.
u comma, no, we don't have any perpendicularity condition. What is z plus z bar? X plus iy plus x minus iy. What's it?
Times of real part.
2x. So it means it's 2 times of real part of z. Same way, here you can replace it with norm u square plus norm v square plus 2 times real part of inner product u comma v. Okay, that's how we got it here. Okay, and then what is the relation between real part of inner product u comma v and modulus? The same thing. So what is mod z? Mod z is x square plus y square, right? So you can see that real part of z is x, right? So x is obviously less than or equal to modulus of z. Is that clear? Right? So here from this you can see that real part of z is less equal to mod z. So the same thing you are applying here. Real part of u comma v is less than or equal to modulus of this value. And then again here Cauchy-Schwarz inequality you can apply. So Cauchy-Schwarz inequality says that modulus of inner product u comma v is less than or equal to norm u norm v. So you apply this property here, and then you know that this is norm u plus norm v whole square. Okay, so this is one part. So this exact same thing you can again do, okay, with u minus v. So when you have u minus v, then you will have a similar thing. So again norm u minus v whole square, you can come up again that this is less than or equal to norm u plus norm v whole square. Here some proof is missing, I guess. Norm u plus norm v whole square we have got here. What did we miss? Here only we have proved norm v whole squared in general is less than or equal to norm u plus v whole square. Only this part is done, but this is the proof of something else, right? This is parallelogram inequality we have mentioned. So what we have proved, norm u plus norm v whole square is less than or equal to norm u plus norm v the whole square. Okay, so remember when we had u and v orthogonal, then they are equal. If they are not orthogonal, then this is what we are getting. If they are not orthogonal, then this is the thing we are getting. They are not equal, we have an inequality. Okay, so the other identity we are having here is norm u plus v whole square plus norm u minus v whole square is equal to 2 times of norm u square plus norm v square. So this is parallelogram equality. Okay, so this is something we are seeing here. I guess the name I mixed up here. So here you see that when we are splitting these things entirely, then here you have same identical terms which can get cancelled out, and then what is remaining is 2 times of norm u square and 2 times of norm v square. This is parallelogram equality. Okay, so we have quite some identities here. So using Pythagorean theorem, you have u perpendicular to v implies norm u plus v whole squared is norm u squared plus norm v squared, and then you have the orthogonal decomposition of vectors, and then you have Cauchy-Schwarz inequality, and then you have, this is the parallelogram inequality, and this is the parallelogram equality. Okay, so these are the things we have seen. Okay, one last problem for today's session. This is a very straightforward one which we have done similarly in R3. So in R3 we have done here. Just go through it once. We are going to apply the exact same technique for a vector in C3. Can you all tell what is the first step? So let's call this as U. Let's call this as V. Find all the vectors in C3 orthogonal to both U and V. Okay, so let W equal to X comma Y comma Z in C3 such that U is orthogonal to V W and V is also orthogonal to. So what's the first step? Comma X comma Y comma Z equal to 0. What will you get? Can anyone say?
X plus iy equal to 0.
No. Let me quickly recall the definition. U1, U2, U3, V1, V2, V3 means what is that you will have?
X bar
U1,
plus
V1 bar.
IY.
Yes, yes.
X plus IY bar equals to 0.
So you have X IY bar equal to 0, or you can take complex conjugate and replace it with X
Ma'am, how
plus
X bar?
bar Y. This is the definition if you remember. So U1, U2, U3. V1, V2, V3. What's the definition for Cn? U1 V1 bar plus U2
plus
V2
U2
bar
V2 bar.
plus U3 V3 bar, right? So V1 bar is x1 x bar and V2 bar is y bar, V3 is, here you have U3 0, so this terms is 0. Okay, so I can either write it as 0 and take the whole complex conjugate and write x is equal to I bar y. So this is either you take this form or this form. This is easier to calculate what is x and y, so I have taken this form. Okay, so I'm simply taking, if this is 0, then you know that x plus x bar plus I y bar whole bar equal to 0, and the whole bar is nothing but this term. Is this clear how I got x plus I bar y equal to 0? Yeah.
Yes, ma'am.
And what is I bar?
Minus I.
So you have x minus iy equal to 0. This means x is equal to iy. Okay. Similarly, what is v comma w? So here you have v is 0 comma I comma 1, and then w is x comma y comma z. So this again gives you bar plus z bar equal to 0, which implies minus iy plus z equal to 0. Is that correct? Is that correct? Yeah. So I bar, I have straight away written it as minus I. Okay, so I get here z is equal to iy again. Okay, I get z is equal to iy. So x is equal to iy and z is equal to iy. Okay. So in this case, now what are all the set of all vectors? Set of all vectors orthogonal to both u and v is given by, so x comma y comma z, right? So now I can replace. So if I'm replacing y with alpha, then I will get I alpha, comma, I alpha. Okay, so I'll find C in fact. So these are the set of all vectors orthogonal to both u and. So how to find the orthogonal complement? Is that clear? Yeah. Is this part clear for everyone?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, fine. So what are the topics we have did today? We have seen what is an inner product, what is the norm of a vector, right? What are orthogonal vectors, orthogonal decomposition, and the two inequalities. These are the two parts we have done. So on the other two, others, the remaining part we will complete on Friday session. All right? Okay. All right then. So tomorrow you will be receiving the quiz 2 results. Okay, you will get the answer scripts tomorrow. Either today or maximum tomorrow you will get it. All right then. See you again on the next session then. Okay, least square feet. Can you please go through the video I have given in the chat? So the same concept I have explained there also, I guess. So please go through that once. If I have time, then we can discuss that as well. Is that fine, Maheshwaran? Okay, fine then. Thank you and see you all. Bye.
Thank you, ma'am.
Thank you, ma'am.